Hello and welcome to another video. This video is about not the first, but the second time I failed to derive curvature on this channel. I don't really know what I'm doing wrong, because at least in my mind, the logic checks out perfectly, but the mathematics of the universe says otherwise, I guess. I've never encountered a problem quite like this one, so I'm asking for help from the audience, because for some reason, there is a misalignment between my own logic and that of the rest of the universe. Alright, so this is a lot of information, so I'll go quick. So here's the logic of mine that I was talking about. And please, if you see any mistakes, comment on this video. So my approach was to first consider a position vector, f of t, that exists in three-dimensional space. This function can be expressed as a function of arc length, s1. Now consider a point on this curve located at, here's f of t. Consider a point on this curve located at f of s1a. We want to find the circle represented as position vector g of t, this circle over here, that best fits the circle f of s1 at, that best fits the curve, this curve, f of s1 at f of s1a, this point over here. Now we know from geometry that we need 3 points that are not collinear to fit a unique circle. So we will choose f of s1a plus delta theta, and f of s1a plus 2 delta theta, these 3 points, to be those 3 points, and we're taking the limit as delta theta approaches 0. Also from geometry, we know that a change in arc length, delta s, s1 or s2 actually, is equal to the radius of the circle r multiplied by delta theta. Sorry, delta s2 is equal to r delta theta. So that's why we want to express everything in terms of arc length, because we can use this relationship between r and delta theta to get delta s2. So we have the equation for g of t expressed in terms of n hats and t hats, which are orthogonal unit vectors on the osculating plane. And we can also express g of t as a function of its arc length s2. So basically s1 is the arc length of f of t, and s2 is the arc length of the g of t. So we want those 3 points to be on our circle, and therefore f of s1a is equal to g of s2b, f of s1a plus delta theta is equal to g of s2b plus delta theta, and f of s1a plus 2 delta theta is equal to g of s2b plus 2 delta theta, where s2b is the location in the domain such that f of s1a is equal to g of s2b. So that's the setup there. I know it took a while to explain, but that's what I have. So now from our diagram, we can extract this set of constraints in the form of multiple equations in the top left corner. Over here, in the top left corner, we have our 3 equations that tell us that we want our 3 closely spaced points to be located on our oscillating circle. To the right of that, we have 2 arc length differentials. Then we know from geometry that a change in theta is a change in arc length of the circle divided by r. And from the arc length differential formulas, we can deduce that a change in arc length of the circle divided by oh sorry, changing the arc length of the circle is equal to a function of t multiplied by a change in arc length of f of t over here, where the magnitude of dg by dt is actually equal to r. So this is actually equal to r over here. And we could show this by taking the derivative of our equation for g of t, which is f of t of s1a plus cn plus r cosine of t n hat plus ct plus r sine of t hat with respect to t, where cn and ct are constants that describe the location of the center of the circle in the coordinate system of the osculating plane, which lies on the plane described by n hat and t hat, which are both on the osculating plane. Additionally, we have t hat, which describes our unit tangent vector to the circle, constructed from f of s1a and f of s1a plus delta theta. I'll actually show the simplified version on this slide because the factor r over magnitude of df by dt, this thing over here, actually cancels out in the numerator and the denominator. And it's also the same idea with the a hat, the acceleration vector, where you get square terms that cancel out in the numerator and denominator. So we know that t hat and a hat lie in our osculating plane because they were constructed from points that lie on the osculating plane. These points. We also have n hat, which is a unit vector on the osculating plane that is orthogonal to t hat. It's basically the projected perpendicular components of a hat onto t hat. And when you're taking a hat minus that projection onto t hat to get the orthogonal or perpendicular component of a hat to t hat. And then we have b hat, which is a unit vector normal to our osculating plane, which we get by saying a hat cross t hat. Now we can also say n hat cross t hat, but it's a lot easier if we say a hat than n hat, because n hat is a bit more complicated of an expression. So the fact that f of s1a is equal to g of s2b, and f of s1a plus delta theta is equal to g of s2b plus delta theta, and those 2 points lie on our circle, implies this equality where you have the limit as delta theta approaches 0 of this, and the limits as delta theta approaches 0 of that on the right. So if we set this constraint, then we get the equation on the bottom, and notice that it involves an r. We can actually solve for r, but the weird thing is that when I solve for r in MATLAB, I don't get the correct radius of curvature. So that's why I'm really confused, because you would think that you would get the correct r given the setup, but that's not the case. And also, you would think that we need to use the second derivative relationship as well, but we actually get an overdetermined system if we use the second derivative relationship as well. So that's why I'm really confused, and I'm asking for help from the audience. If I could get the help, then that would be awesome. So yeah, that's my request, and have a great day.